The first presentation will be by Levi because he claimed that there is a important meeting right at 5. So we'll have the...
Today the meeting was canceled.
Well, too late. You are the first anyway.
Probably.
So originally the plan was for 7. The number 7 is not confirmed. So
Who's 7?
London.
Oh.
So for 6 presentations in 2 hours, we have about 20 minutes, right? For both presentation and questions. Well, it may go a little different, but if someone takes more, it means it is withdrawing from colleagues. Are we already on recording? Okay. Trying to be very, very quick in opening these things.
So how am I gonna like point to it?
Well, you can navigate us by voice commands, telling
Okay.
look up, look down.
Look right,
Yes.
look left.
And if you do not like it, if you want something more advanced, you can share your screen so that it projects on our screen. It may
I don't think I can because I'm not connected.
You're not? Okay.
No,
then,
it's the internet thing. I don't. It'll be fine. I'll make it work.
Okay. Yes, you can just navigate by word, by voice. So the idea and the procedure is the same as before. While the presenter is speaking, the audience tries to write comments on the printed versions. They will be distributed, and after a presentation is done, there is a session of verbal questions, and even if you do not have time to ask questions verbally, you can write everything that you like or do not like on this paper versions and then submit it back to the author at the end of the discussion session.
Do we have copies for Levi's?
Yes, we do. I will distribute in a minute. And I'm repeating, the credit is given to Javed for printing.
Electric voice
May I request help from Aaron in suggesting the buttons to make it full screen?
F11?
Just F11?
Yep.
Okay. Levi, do you see our screen shared?
Yes, I do.
So I will distribute your printouts. Everyone, please armor yourself with pens or pencils. And Levi, please start for the sake of time.
So thank you guys all for coming and listening to my practice. Can you all hear me all right?
Yep.
Okay. So first I would like to kind of go into the motivation, which is on the top left. And our real motivation for this study is to pretty much understand how the composite of a quantum dot will influence the excited state relaxation from initial excited state down to the hormone LUMO. These systems have been experimentally studied on much larger scale. We are restricted due to computation to a lead caucasianide system with 68 atoms each. And what we do to make the core shell structure is all of the lead on the surface are replaced, and you can see that in the ground state properties of the lead X, cadmium X in the center, where I cut out some of the atoms, and we can see the gray on the interior, which is the lead core, and then the outside is the cadmium shell. And this has similar electronic properties for the sulfur and the selenium system, which is shown with the projected density of state also in the center of my poster, where the projected density of state has color on the background, and that is where I looked at the electron distribution as a function of radius from the center of mass, and that is on the panel B, and we can see that the electronic distribution for the unoccupied states and the occupied states rather deep in the conduction band are relatively similar, where the frontier orbitals for the occupied bands are not. And this can have very big implications for the excited state dynamics, because we use non-adiabatic dynamics to simulate the relaxation. So if we look at the methodology section, which is on the bottom left, we will, it goes over in detail the methodology that we use. In short, we use VASP to do single point calculation after we do a MD trajectory. Then we do a non-adiabatic coupling for the off-diagonal elements in the electronic propagation. And then we use Tully's fewest surface switching copying algorithm to actually do the electronic propagation from the initial excited state. This has been used quite a lot, so I'm not going to belabor the point. What I will show in, what I will explain a bit more in the methodology section is how we analyze the excited state population as a function of time. And what we did here, we used a 4-state kinetic model where we, oh, John, is that a question?
Yeah, I'm wondering, can we scroll down on your poster so it hides the,
oh, sorry.
so hides the title?
He will not be able to.
I just want to see what's on the bottom of the poster.
Did he not email a version to you?
This is a good question.
He's on call.
I will double check my
Pretty sure he
email.
did.
Whoever is on the Levi, would it be fine if you do if you show this
Yeah,
way?
that's good.
Okay.
Yeah, that's fine.
Look onto the program and link to PDF. They all are online. If you look to schedule, okay.
So then we took the 4-state model, and we have 2 intermediate bands, and then we have the initial and final. And we did kinetics, and we got the integrated rate law, and from the integrated rate laws, we can get various excited state lifetimes. Was there a question? No, okay. And we can plot that as a function of time. The last thing that I'll go over is how I simulated IR spectra, or looking at how the bonds vibrate. And that I just took, I did it pairwise on all the atoms that were within a threshold, and then I did a FFT on the displacement. And that is the figure on the center bottom with all the lines, figure 4. And we can see that the modes are a bit different. Notably, if we look at the inserts, there are peaks from about 100 wave number to about 275. These are important because these are the peaks that we believe are interacting with the that couple the electron and phonon, which mediate the relaxation. So that is kind of the methodology. So if we look at the ground state, we already looked at the ground state property. So if we look at the molecular dynamics, we can see that the absorption for the for 0K and the first 300, the first 30 frames qualitatively agree. The only thing that we miss in the ensemble approach is the low band. That kind of gets washed away due to the reorganization of the ions. And then I already explained the simulated IR spectra. So if we go to the electronic dynamics, which is in the top right, the first thing we can see is the population, the density of population times the density of states with the average energy of the electron and hole superimposed. And from this, it's relatively difficult to see how the dynamics, to compare the rates of the dynamics. So if we look at figure 6, this is the normalized energy in respect to the initial exciton, and we see that selenium has about two-thirds the amount of time it takes to get down to the homo-lumo, or nearly zero relative energy, and this could be used to enhance things such as multi-exciton generation due to the fact that we're not losing our energy as fast into the bond vibrations as we would in the lead sulfide, cadmium sulfide core shell structure. And this has all 4 simulations. So currently I did 1.5 and 2.0 excitation compared to the homo-lumo gap. In the figure 5 and figure 7, I only showed one of them because they're very similar. The only thing that changes is the rate and the lifetimes. So if we look at the fitting the excited state population, we see that the 4-state model has very, very good agreement, which means that our excited state lifetimes are somewhat reliable, which is in table 1. And we can see that for almost all of them, the heavier selenium is around 1.5 to 2 times longer to relax for the excited state lifetime. And the last thing we did here was we looked at how the autocorrelation function, do I need to explain the autocorrelation function, or should I leave that for questions? Hello?
Just ask if anyone wants to hear about autocorrelation function and count until 3.
Okay, so I didn't hear anything. What the autocorrelation function does is it can relay back how much electron-phonon coupling there is. And if we look at the 2 figures in figure panel A and B in figure 7, the one on the left, panel A, that is an order of magnitude smaller than the other panel, which means that lead sulfide, cadmium sulfide has a lot more electron-phonon coupling than the cadmium sulfide and lead sulfide structure, which is another reason why the excited state loses its energy at a faster rate compared to the heavier ion. And then the conclusions, in the ground state properties, we showed that it's a quasi-type 2 core shell structure. We can use what elements are in the core shell structure to tune the relaxation rates, and this could be helpful in either slowing the relaxation rates if we want to try and do multi-exciton generation, or if we want to have the excited state very short, so it can be an emitter, you could use that. And then future work, it would be good to compare the last cacalgenide, telluride, to see if the rates are reduced as well due to the larger mass. And then I didn't remember, whoopsies. and I messed up on my second conclusion. That should be acknowledgements. And then I didn't really finish that because I didn't want to put the wrong grant. So if there's any questions, please feel free to ask.
Okay, well, thank you, Levi. Any questions? Levi?
Can you turn the camera to the audience?
It may break the connection. If you do it.
Oh,
too
okay, never
frequently,
mind then.
It's not a good idea. So, question.
Never mind, don't do that.
So, you are comparing sulfur versus selenium, and selenium is consistent with longer relaxation, right?
Yes, selenium is a little bit less than 2 times longer. Like 1.5 to 2 times longer.
I have missed what is the explanation why.
So if we look at the figures 7, then and we look at
two figures, only Levi.
yeah, so figure A and figure B. Right, panel A and panel B. 4? What's 4?
You have 2 figure 7s
this
each with
one-
2 panels.
Oh,
supposed to be
sorry.
8,
Yeah, no, my bad. So the second figure 7. My bad. The autocorrelation function, or if we go more in depth on what autocorrelation function is, we look at the initial excited states, and then we take the energy difference between those as an ensemble approach, and then we take that like trajectory. So if we have 500 steps in our non-adiabatic dynamics, we would have 500 energy differences, and then we perform an autocorrelation function where you take all the index, all of the you take the square, the sum of the squares of every difference, and then you shift the function, and then that will oscillate if there is correlation, and the oscillation is due to the vibrations of the ions, which means if the ions the ions move, and if the electronic states change a lot, that means that they're highly coupled. And since the autocorrelation function is virtually just a multiplication of the energy differences, that means that the higher the autocorrelation function, the more the phonons interact with the electrons. And a fast FFT is a fancy way of multiplying those functions to get frequency domains out, which means the higher the autocorrelation function, when you do the FFT, the greater the electron-phonon coupling is. Does that answer the question, Dimitri?
Not completely, but gives a little more insight.
Well,
And
technically, I'm not sure that I really agree with your explanation. Again, looking on the second figure 7, right?
Yes.
My understanding, you just rely your explanation by the difference in intensity of these peaks after the Fourier transform is done, right?
Yes. I could also add the average nearest neighbor and nearest neighbor in the non-adiabatic coupling, like the matrix, and for sulfur, it is around 2 times greater than it is for selenium, which that's also another reason why the relaxation is much faster, because the non-adiabatic coupling terms go directly into the SSH algorithm, which then has a higher probability of relaxing to a lower state.
Levi?
Yes.
So you, in the center, figure 2, right, you do have a schematic diagram, but
Yes.
it is only one case. You may, would it be reasonable to show schematic diagram for sulfur and selenium
No.
and
no.
show how they are different, or the
So, if
relative offsets will be approximately the same.
So if you look at B in figure 2, panel B, there are 2 panels within panel B. Do you see them?
Yes?
And qualitatively, they agree, which means that the schematic diagram would be virtually unchanged.
Okay, so electronic structure and spatial localization of orbitals will be approximately the same.
Yes.
Okay.
So, related questions in a sense that when you were going to your motivation, I think you really didn't articulate very clearly which questions you are addressing with your research presented on your poster, right? So what exactly is a question you want to answer? You never really told. You tell once again, so what was exactly, like, about motivation, why is it important and why you really looking on these core shell structures? I think you kind of told it to us, but this is too general, right? So I don't understand what exactly is the question you put to answer with your specific things which you are showing in this poster.
Yes, I got your question. I need to think about it because that's a good question. Can I think about it and tell you at a later date? I don't want to go into the next presentation's time.
The situation looks like this. So you are a captain of a ship, right? And you getting in a sea, and suddenly in the middle of your trip you're telling, well, I have no ideas where I'm going to go. Right? So, like, you're completely out of your navigation or anything. You don't know what exactly your destiny. And so, this is a little bit strange, right?
One thing that I would assume, or that I got out of it, which I don't know if that was the original question that this was going down because I inherited this project, is since the electronic structures are qualitatively similar, what drives the difference in the relaxation rates?
Okay, good.
And that can be explained by looking at the FFT of the inner ionic bond distances and the FFT of the autocorrelation function. And I should add on here the nearest neighbors of the non-adiabatic coupling, because all of those would say, although the electronic properties are very similar, these properties are not, and we could try and exploit these in future applications.
Okay, good. So, like, the beginning of the story, if you look again, return back to the papers from experiment on the structures, right? So they were showing that these core shell structures exhibit higher efficiency for the carrier multiplication. And in particular, it was showing that in lead selenide, it's much quicker, or how to say, more efficient, comparing to lead sulfide, right? So something really making these materials be more efficient for carrier multiplication. You are not addressing the carrier multiplication, you are addressing the relaxation, right? But in this experimental papers also say that due to the core shell structure and this electronic structure too, right? Which is your pseudo type 2 structure. So they expect that it's really due to the slow relaxation compared to other materials, right? So your relaxation is slow, and again, comparing lead sulfide versus lead selenide, it's supposed to be slow in lead sulfide, cat sulfide, rather than, backward. It should be slow in lead selenide, cat selenide, rather than sulfide, right? And this provides higher carrier multiplication efficiency. So in experiment, right, so of course their main goal in experiment was to really see and kind of investigate the carrier multiplication. And this is not what you're doing, right? So you start with your relaxation rates, but you probably can also mention in the beginning in the motivation when you're saying how important these systems, right, really highlights the idea that it was shown that carrier multiplication, specifically in these materials, really more efficient comparing to just lead selenide or lead sulfide structures without the shell, right? And again, experimentalists already know the reason. They said, oh, it's because the relaxation rates are different in these systems, despite that the electronic structure is similar. But now, you, with this research, trying to really answer the question why the relaxation rates are different, and really prove that relaxation is different and what is the origin of such difference in relaxation rates for these materials, right? Again, based on the idea that the electronic structure is very, very similar. So this will kind of, start your presentation and will put very clear ideas what is really main things to look on, right? And I think for people, for you it will be easy to navigate through your poster, so then again you will highlight the main ideas, like as you already mentioned, my figure 1, 2 showing this, and the other figures are more like supplemental things, right? And for people who will listen to you also, it will probably have more sense rather than just going through figure 1 showing this, figure 2 was calculated using this and it shows that, right?
Yep.
Okay. And it looks like you said like you will add some additional figures there, right? For, you mentioned that you will also add your, what are you going to add again? You said that you're going to add something.
Average non-adiabatic coupling terms for the off-diagonal elements.
Oh, you mean it's another table or what?
Yeah, just a table.
Okay. I don't know whether you really have space for this.
Yeah, that's the problem.
So I suggest you have a figure 7, another figure 7, right, the top one, where you have electrons and holes, and overall dynamics looks very similar for both electrons and holes, right?
Yeah.
The figure where you're showing this applicability of this kinetic scheme.
For state
right?
model.
So you probably can take out either electrons or holes and then just say that we see very similar things with slightly different parameters, and you can leave your parameters in a table showing that kinetics is there, right? So the diagrams clearly behave very similar, so you can take one of these figures, leave only electrons or only holes, up to you what you choose, and then and then you will have more space for adding something else. And go back to the Dmitri's question, I think you kind of answering, but really think about, like, this is your central point, right? To explain why the relaxation is different with these materials, despite that the electronic structure is the same. And the answer is not just, yeah, it's different, but the answer should be really why, and you should be clear, like looks like you have enough data here to support it and really explain it, but really think about how you really construct your discussion, making it really as a central focal point, so people will not ask you 10 times, like, so why is it so?
Okay.
We're done.
More questions to Levi? 1, 2, 3. If not, let's thank Levi once again. There is a community service for champion of printing Jabot. Please collect the comments to Levi and scan and send it to him. So the next presentation is by Austin Brewer, who is
Just pulling that up.
I will pull. Good.
Yeah, looks good to me. Alright, so thank you as well for being here and letting me practice in front of you. As you see, the poster in front of you is definitely a rough draft at this point, so bear with me, but I'm excited to hear some feedback after this presentation. So my project that I undertook was the nuclear reorganization of manganese-doped quantum dots in perovskite solar cells. And the main purpose of this research and what I've understood from it is just finding a more stable way of having these dope systems, specifically with transition metals. So with perovskite quantum dots, when they have these big complexes, there tends to be some instabilities within the quantum dots itself that lead to problems in the system, like stability, how long those quantum dots can actually last in the perovskite cells, and then also just with their light emissions and absorption patterns, so the photoluminescence and the yield that's associated with that. So the diagrams I have presented there are simply just models of the part that we're most focused on with the manganese dope quantum dot. And those are just the octahedral setups of the manganese and the bonds associated with the bromines in front of it. The abstract I really plan on shortening at this point, obviously, on here. It was the abstract actually submitted to the conference, but if anyone read that on the conference, I'm sure they would walk by my poster pretty fast. So I do plan on shortening that. But going into the methodology section, there's still a lot of it that I do need to understand and get down, but the basis of it and how we are actually going to kind of measure either the photoluminescence, the yield from that, or also the stability of the molecule comes from, I believe, 3 main sources. The first one is just a comparison to Marcus theory and how we should expect electron transfers in that octahedral setup between the manganese and the bromide. Just comparing it to what's known with Marcus theory and the observations that are either made through estimations or other programs like MATLAB software like that helps us understand what the transitions might look like in a model. Just comparing those two is really going to be beneficial and help us see what the stability is like for this quantum dot and a general sense for transition metals too. Also using density functional theory, this is one area that I'm definitely lacking in knowledge in. If you have any suggestions on how to kind of approach this idea, please let me know. From my understanding of it right now, this kind of just, again, associates the actual reaction, or not the reaction, but the doping mechanism with how the bonds are going to be, I guess you could say, moving, contracting, etc., and how those bonds are being more stable with electron transfer. Again, that's kind of what I've understood from the density functional theory as of this point, and I know that has a lot more to deal with what Aaron Ford's done with his research that I'm using as part of my project in the ab initio diagrams that I have over in the results section. And then also through first principle calculations, just to actually understand the rigor and mathematics behind the stability patterns, the light emissions for this quantum dot process. So that's the methodology that I have set up right now as I've understood it. There's obviously more equations and everything that needs to go in there, more understanding from my end as well, but that's how I have it set up right now, is actually measuring and getting quantitative and qualitative proof of there being more stability at one certain point or another. So then going into the results section, split it up into 2 sections. The first results section is a lot of the work that I did in Physical Chemistry 1 or Chem 364, and that was just the estimation through MATLAB software of what the most stable energy ranges are going to be for these quantum dot or this manganese dope quantum dot. And the figures that I have there, I know my type is very, very small right now, but basically just from top to bottom, the top is just the electron transfer rate over time, and what we're seeing is that at varying levels of initial momentum in the system, or energy that's initially present in the system, we're having more and more stability as there's increased energy in the system. And there is kind of this equilibrium point where it is, limited only to that, where there's electrons being transferred and the stability of the quantum dot being around the 75% range, if I remember correctly. Second one down is just reaction process, or the reaction coordinates, seeing as it goes forward, you can kind of see how this equilibrium kind of starts to shift with the stability of the quantum dot molecule. And then the last one is just rate of reaction and how it's actually going throughout its process in the quantum dot and the stability of the doping. The table underneath it just kind of shows, again quantitatively, the pattern of adding initial energy to the system and how I measured it with the MATLAB software, just using those, messing around with the different energies that are in the system initially. And you can see that trend, if the numbers were a little bigger, that shows in all the graphs too, is as there's more energy initially in the system, it becomes more and more stable with the photoluminescence as well as the bond lengths and just, I guess, general stability again within that molecule. So then the second results section, and again, I gotta give all credit to Aaron Ford right here, simply because this is a lot of his data that he's been using on this, and I still have yet to run this software myself or the script along with it. But this is the comparison of the Marcus theory, and this is a more rigorous and actual specific understanding of the values associated, again, with the stability, photoluminescence, and those observables that we're trying to see with our prediction of the molecule. And again, that just from my end, I definitely need a lot more kind of rigor and understanding in, which I plan on actually meeting with Aaron Ford and going through that just to get a better understanding. For the conclusion section, I've yet to develop any conclusions based off the information I have right now, so I just left that blank. Just something that's going to take a little more logical thought for me as we get closer to the conference. But basically, again, the goal of what this project would be is to get an ideal or optimal situation of what transition metal doping in quantum dots in this setting is going to be like, in the cesium lead bromide setting is going to be like. And I'm sure the conclusions will just kind of be based off that and the initial factors that influence how the stability and those observables are affected.
Okay, good. Thank Austin. Any questions to Austin right away? Let me make a little comment, and maybe it will inspire more vivid discussion on these rights of author I want to add. So it is how I understand what Austin did present. He has a code for quantum dynamics calculation that he runs or intends to run twice. First time with parameters from the top of the head, educated guess here, and then from parameters that come from the ab initio calculations. Parameters are here, but another section that will look approximately like this one should be placed next to it. So it is like 20% of most interesting and important results are still missing. I'm done. Please keep asking questions. Which is?
So, for your parameters, right? I understand this is not part of your work, but you probably expect this type of question.
Yep.
So, how these ab initio parameters were obtained? You don't need again to know all the details, but at least you probably need to understand in general and say right words if there will be this question.
Right, and specifically like that data table kind of down on the second data table and the second result.
Well, I would start with what type of parameters, because again, here you're just given some numbers and some abbreviation, which doesn't tell me anything, right?
Right.
So I need some physical meaning. What type of parameters you were using? And then again, how this you think were obtained from DFT calculations?
Yeah, so the parameters, again, from my understanding, is, which you're completely right. That's something obviously I just need to know more about. From the parameters that I understand, it's the same kind of system of like the energies that's developed in the quantum dot.
What do you mean energies? What kind of energies? Electronic levels or what?
Yeah. So like excited.
Electronic structure?
I'm sorry, what?
Electronic structures, the levels.
Right, so like the excited states that are within the electronic structures themselves.
And
How,
then this information is used for what? Because again, well, probably right now it's really hard for you to tell anything because in your methodology, right, you need to have formulas, not
Yep.
some abbreviations of the code, right?
Yep.
This is kind of your business. No one really cares how exactly this was done, right? You need just to show main formulas, right, and clear interpretation, or how to say, clear vision of parameters which are used in these formulas, right? And then say, well, here is this parameters. We just choose, this is kind of, we were choosing from this limit, from like trying the smallest, the largest, or whatever you were doing for your first part, right?
Yep.
And then here our more realistic parameters based on DFT model, really getting from our initial calculations, and then maybe you go. But again, for your parameters, right? So we're just looking just on your figure, which you're showing with these two parabolas. Looks like you need this, how to say, the height of the barrier, right?
Yep.
To overcome. So then again, I'm not sure, like just knowing the electronic levels, how is it connected? How are they connected with this picture? Now suppose you got this electronic level, so then how is this exactly connected to the things which you have in your model?
I'm unsure at this point.
Let me reformulate the question.
Yeah.
You try to answer it once, and then you request help from Aaron.
Okay.
If it is hard. So you are showing two parabolas, which means two electronic states, not hundreds, like Levi was showing recently in his work. But in addition to energies of electronic states, which is likely just minimum of the parameter, you need all these curvatures and offsets of horizontal offset of parabolas. Where are they coming from, or how do you get them, or how do you want to get them?
Right.
So
So
please address on this.
yeah, and I'll try to answer it to my best ability. The offset of the parabolas, from my understanding, is the distances based between the different bonds, and that's, you know, what's causing the actual offset, and that's what the electron transfer and the ground states between them. That's the energy that we're
So
trying
in
to
the
measure.
DFT calculations, right? So you're not just getting the electronic levels, because this is typical. You optimize the structure and get electronic levels, and you're taking your two levels of this, like two parabolas would be your level 1, level 2, right? But again, you need, as Dmitry said, and again, you even without formulas, you can use your figures there, right? So you need to know curvature and how much they're shifted.
Yeah.
So you already said that then you need to run another calculations, kind of artificially maybe changing the bond lengths between atoms and getting new electronic structure or new energies for each case, right? Which kind of will provide you the
Some
potential
different
surface,
curvatures.
the curvatures of these parabolas.
Right, and then you can
Okay?
compare.
But then still the shifts.
So if you can answer, please answer. If you cannot, please ask help of your authors.
We just learned a lot of this today, Austin. We're restarting to is the potential energy stuff. Like we literally
I
just
might-
went over it today.
Yeah, I might take some help from co-authors if they're
Yeah,
willing
that
to.
is my question as well. How do you get the two different reaction coordinate, RG and RE?
So
I'm sorry, what was the question too?
Alright. There are two reaction coordinate, RG and RE. How you get these differentiate these two coordinates?
It was the same coordinate.
Aaron?
Because the same bond.
would you
I mean,
like to
bond
go
between
to the
the-
board and just index so that everyone understands better?
It is not actually by atomics.
So, how we kind of constructed these is this point here is the ground state of the geometry optimized perovskite quantum dot. And what we did, or what would be this way? So that's the bottom of this parabola. And the bottom of this parabola is we looked at a specific excitation that's possible for the system. So for this one, I think it's the metal-metal transition. So what we did is we changed the spin configuration of the quantum dot. and then we did a geometry optimization to get this one. Then we just did some Fairweave calculations. But for this one, we took the excited state geometry and gave it the ground state electronic structure. And then for this one, it has the ground state geometry optimized structure with the excited state electronic structure. So that's how we get the 4 points, so we can make the 2 parabolas for the potential energy surfaces.
Aaron,
Yeah, Levi?
what's your internal coordinate?
It's one of the bond links of the the bromides around the manganese.
Aaron or Austin, can you show this bond links on the diagram near the abstract?
Yeah. So.
Dimitri, can you zoom back in?
Yes, sure. Thank you for giving me instructions what to do. Please keep going.
Yeah, so I mean the bond links that Aaron was just mentioning is just the bond links between, like I said, in this octahedral setup.
And it's just one of them, so in this case it's...
Well, in average, they're not very different, right?
well, one of them is. It's a little longer than the other ones, but...
Well, yeah.
We're working on that.
Those which are on the plane, you taking those which are on the plane?
Yeah, well, just to generate this picture, I just did one of them, but I've recorded bond distances for all of them, so we can make surfaces for all of the bond links. So does that clear up any ambiguity?
Well, and then I'm kind of confused, and it's really hard to see anything on the figure. Actually, do I have this figure? What is this figure?
It is the same as upper figure.
Oh, okay. That's
Yes,
why you
better
don't have it here,
resolutions.
right? Okay, good. And again, for the conclusion, if you're comparing, like Dmitry said, it's probably better to show both of the results for your just hypothetical parameters, right, and ab initio parameters. If you compare them, could you again tell a little, like, what exactly is the problem to take your hypothetical parameters, right? Are you really learning anything from it in a sense that it's not just educational, but really doesn't give you any physical meaning to explain maybe then your right panels, or maybe you use some knowledge from your parameters, hypothetical parameters, to interpret your ab initio behavior or something, like, because right now it looks like, oh, we have done this, we have done that. That's it.
Yeah.
So
What's the connection?
are there any ideas how it can be connected, and do you really see any reasonable results or anything reasonable from your first approach?
Again, I don't know enough right now of the AB initial to give like a definite answer. It's something that like
But for these parameters, like, of course you are more flexible because you're really varying them, right?
Mhm.
Since it's up to you what to choose
Right.
from this limit to that limit, right?
And like I said, like in the estimated one, what I did notice is just the trend of, you know, getting to some kind of optimized point, you know, where
Okay,
there is.
but then the trend and getting optimized point, like, is the prediction based on your optimized point just playing with these parameters? Are they coincide with what is seen for the ab initio calculations? I don't know. Like, if you can see optimized parameters for your
No. Yeah,
just
and
parameters, right? So is it kind of in agreement, or at least is it close to something which you also can see in your parameters taken from DFT calculations?
yeah, and I get what you're asking, just to make sure like, that they're comparing and actually.
So you have done.
I haven't
mean,
done it yet.
You
Haven't
can,
done
but
it.
you didn't. Okay.
Yeah, haven't done it, and I do have
Think
the
about it.
script. Yep, exactly. So.
More questions?
And what is the font size are you using?
Right now, I mean, it's. I varied it a little bit just because.
Well, just give me the. Do you remember which font?
20?
Yeah, I
20,
think-
18, 12,
I think I used 25.
25. So the rule is you should not use less than 28.
Okay.
The perfect would be 30. And actually,
Okay.
this is a size which is larger than what you will see. Really, look on your. This size is probably about 1.5 times larger than actual size of the poster.
Oh, really? Yeah, that's
So you
true.
can see how small it is.
Right.
It definitely doesn't work. And also, I think your poster looks like it's a square rather than an elongated one. So check the sizes of the posters,
that, yeah,
because
I
they
did-
have a fixed size of the holders.
Yep.
And if your poster will be much larger, either in one size direction or the other,
If I remember
will be
correct.
you will have a trouble to just set it in.
Yep.
Because you will be not able to fix it.
So they had the size requirements that was sent out through both of you as well, which was I believe the 4236.
But it looks
Yeah.
like it's probably not in this requirement, so be sure, because otherwise, when you print it, it would be either too long, and then again, you will have a trouble to fix
Yeah.
it on a holder.
And I can double
This is
check.
the
but-
maximum size, 36 by 48. So you can.
I mean,
make
you always can
anything
do
in big.
smaller.
Yeah, you can
Small
make
is not a
smaller.
problem, big is a problem.
Yep, I'll double check. I did remember, I believe it's like 4034. I changed it to
Yeah.
just to be a little under, but I can maybe make it even smaller than that just to make sure that it will actually.
It's just a note, so because it's your first kind of time
Yep.
doing it, so it would be good to know.
And I guess 72 font size is like 1 inch in real size. It's kind of like that. So
Okay.
you can have an idea of how long, how big
And
it should
also
be.
save the space for acknowledgements.
Yep.
There will be managers of federal agencies who give funds,
Yep.
and they will check for acknowledgements.
Yep.
And also Aaron for that.
Huh?
Aaron?
No.
Aaron is
Kind.
both.
Oh, it's called Aaron.
Yes.
And you also need affiliation, right? So you need to say where you are, not just names. You should have like North Dakota State
Okay, yep.
University, Department of Chemistry, Material Science, or whatever it is.
We are a little short of time, but I have an important question.
Yes.
What is the main observable? Upon you complete ab initio plus quantum dynamics, what are you finding? What are you trying to get from this calculation? What is the main number that you are going to report as an output?
From my understanding, photoluminescence qualities.
It
And
is
I
correct,
don't-
but it is far-reaching goal. Right now, you are not computing photoluminescence.
Okay.
You're computing rates of transitions. Same as Levite does.
Yep.
Rate of relaxation or rate of transition.
So then we should be measuring then from that calculation.
And your table in the middle column, most likely it contains this data.
Just the percent yield or
No, rates.
the reaction rate.
Reaction rates,
Okay.
yes. More questions, one?
Actually, yeah, in this table it's unclear. When you say electron transfer, what exactly you measure? Electron transfer couplings, electron transfer rates?
And Aaron may correct later, tell him, is there electron transfer between these specific states or not? This is yet to be checked.
Well, just by definition, you need to be more specific.
More questions, one? More questions, two? More questions, three? Let's thank Austin once again. So, please collect, Austin, please collect feedback and implement it. So, the next presentation is by Christian News. Is it visible? So please start and I will distribute the.
Okay, so my poster is based off the study of a dye-sensitized cesium lead halide peroxide photovoltaic. So to start, I give a quick intro into what a perovskite is. It's can be any combination of different molecules as long as it's in a structure of calcium titanium oxide 3. This allows us to mess around with different composites of all of this, given how easily, as long as it fits within this same framework. Because of this, we can study further with our cesium lead halide for photovoltaics, but perovskites by themselves cannot achieve this. So we have to use an organic dye to continue this photovoltaic possibility. Here's just a diagram of the perovskite structure and the organic dye structure, along with the two scenarios that we're going to go through with, showing how the through space scenario and a chemical bond scenario would move forward. I had not gotten into methods. I need to discuss more with you, Aaron, because I don't understand a whole lot. But the basics, because this was last semester more of a learning thing, I really optimized it to be simplistic. So the curvatures of the two states are the same, and they're both at the same energy level, just for simplicity's sake for me, which I need to add in the more better details of that. So this data is from those two scenarios of those of each state being the same. So the data is, as I change initial momentum, is that if the initial momentum is also showing the different temperatures, and then I also added the reaction yield from transmission probability. And then right here is the in the last column is the rate of reaction. As you can see, as you increase the momentum, the rate of the reaction will increase, and the rate of the reaction is the electron transferring over to the next electron state. Here's just the rate of the reactions graphed onto the temperature rate of reactions versus both kinetic energy and time. As you can see, it increases and levels out at a certain momentum, which you can see in our table. As you continue to increase, it will start leveling out and even start decreasing a little bit, which you can see when you're running the program is at some point that it has enough energy, these electrons, to come back down or come across again. But that's probably partially due to my oversimplified scenarios. Here is just the show that how as more electrons transfer over, you see a shift in everything. Here's if nothing is able to transfer over, there's not a momentum, and you can see that there's only one singular position over time. But as more and more transfer over, we start seeing a shift in the configuration, and this is where a second wave will start showing up. Not entirely sure I have correct conclusions, but what I see here is that the through space gives me a better reaction yield and at a lower temperature. But the electron transfer, the shift in electron field is observed, increases more as electrons that are transferred, and through space has a quicker rate of reaction.
Okay, well, thanks, Christian. So, presentation is open for discussion. Any questions?
How big is your simulation cell?
I can't remember off the top of my head right now.
But it
you are not
is
doing
what
the
is.
calculations, right? I mean, your structures which you're showing, this is not really your work. This is work of Erin.
What I did was just a very simplified parameters from
Right,
Aaron.
I mean, so that's why, yeah, this is a valid question,
Okay.
but looks like it's a question to his co-authors.
Yeah. Which as I said, I need to do more discussion with and add more of that data to give a better picture of the actual.
But again, the approach here, because you never know, like, yeah, you have made, like, people see that there are many people in your author list, right? So, which means some people have done something also,
Yes.
right? It's not just your results. But you are presenting, right? So it means you should understand what's going on.
Yes.
So you can just say that, yeah, this part was done by this author, so that's why you probably don't know all details, but at least main ideas you should know, right?
Yes.
Like what software was used to calculate, right?
Yes,
Yeah,
and
maybe size of computational cell, because it's really simple to just one question to ask.
yes, and I know that. I just hadn't had a chance to go to Aaron.
And here again, the parameters, what kind of parameters you using? You also were, like, here you're not using this
We use
parabola.
I use straight MATLAB. So, but he
So
sent me emails.
No, but in
sometimes.
terms of method.
Let me, on the right of author, give a little disclosure that will facilitate the discussion further. And maybe it's also a question to Christian. I will not take his bread of answering. He mentioned that as an approximation, curvature of two states were taken the same. So he is in some sort following up after Austin, and he's also using the same parameterization of two electronic states with an influence of nuclear degree of freedom. So the immediate question we can ask Christian in this respect, which of two states does he model? Because as we saw from the talk number 1 today, from Levi, systems like this, with about 100 of atoms, have about 100 of active orbitals. How does Christian or his co-authors select which pair of states to select? So which states? And then what is chosen as a nuclear coordinate? And so please keep speaking and explaining.
If I'm pretty sure I'm understanding this correct, and if I'm going to say this correctly, the state we'll pick would be the ground state of the perovskite, and then we're moving to an excited state of the organic dye. So we're going to be basing mainly off the ground state of the perovskite.
Okay, so these two states that you model correspond to charge being localized on either one or another subsystem.
Okay.
Those are two systems that corresponds to strong charge transfer. It is what understanding is, right?
Yeah.
Okay.
But how you make your ground state being localized on a perovskite? I mean, from my point of view, it's not necessary. Like, it can be orbitals of the dye being already as your, most electronic state. Possible. And yeah, probably it's not a question to you. It's probably to Eric. Is it you who is calculating this for the DFT calculations?
Yeah.
So how you know that your ground state is really on a quantum dot?
The electron? Or the electron density is on the perovskite.
Yes, on a perovskite, yeah. Well,
Yes.
it
So
can be
the-
on a die, right? So are you really fixing this density? Are you applying constraint DFT? Or just naturally the ground state on a perovskite?
So as far as I understand, the situation is after there's an excitation, you have relaxation to the HOMO-LUMO. The hole is going to be, there's going to be a hole state on the die. So your HOMO is going to be localized on the die, and your excited state in the LUMO is going to be on the perovskite.
Well, in
So
this
those
case,
are the
if
two
you already know that your HOMO is a die and your LUMO is a perovskite.
Let me translate
But this is not necessarily always
Let
the
me
case.
translate the
You
question.
change the molecule and it might be not HOMO on the die anymore, or
Um,
LUMO on the die anymore.
Let me translate the question. Was it requested by investigator who ran this simulation by you that charge is localized on either one or another system? Or it was an observation after inspecting of available orbitals that ground state has localization here or there?
Second.
Observation.
Yes.
Okay. So means because it said like, so here is your HOMO-LUMO for your die. I mean, so yeah, let's say this is die, this is your HOMO-LUMO, and of course the balanced conduction band for the perovskite, right? And you saying that what you see, it's like you saying that it's going somewhere like this, right? So this is a perovskite and this is a die. So means this is LUMO of the die. Your gap is really between die and perovskite. And it can be like this, right? So these levels can be shifted either through the, for example, you can change the molecule which is connecting these two guys, or you can just change the molecule and then the levels can be shifted. Or you can, for example, rotate and connect it to a different surface with a different symmetry. Or maybe even changing the size of the perovskite. This alignment of these levels might be changing, right? So it's really not obviously that it's always this case as we show.
It would make for a good paper.
But this is kind of also a detail. Probably you need to clearly explain that. Just for this system, you see this specific electronic structure, right?
Yeah,
Which
but I
allows
guess-
you to say that in your case, your HOMO is on the quantum dot. On a perovskite dot, it's a dot, right? And then your the LUMO is the die orbital, right? So then you say, well, electron goes to the die. And the whole
Or other way around. Die goes,
or whatever.
hole goes to the die.
Right, yeah.
But yeah, well, initially we just chose those two models to simulate like limiting scenarios,
And
like
this-
full connection and
Right,
connection.
but this electronic structure is not changing. Like you always see your HOMO-LUMO being as a die or the quantum dot, independent whether they're connected or not.
Yeah.
Probably you also need to ask him some maybe electronic structure or schematic representation of these levels.
I need to dig through emails. I'm pretty sure at some point there was an email stream with Aaron and Dimitri with some schematics of that.
More
Yeah,
questions?
putting in some part charge images would help save a lot of questions. But I do have one question. So in your yellow and green figure that you show, the yellow figure has only one blue line and your green figure has two. What is the significance between those two?
The significance between the two, so in the yellow figure is just showing how when your momentum's not great enough to push over the electron to go over to the next state, it just stays within that one state, and it'll just move back and forth between in that state, and that's why you just see one wave. But when you do give enough momentum to get over that activation barrier, basically, as more and more comes over, you start seeing another wave with the electrons showing with the yellow in this one. So the blue is the initial, and then as they start moving over, you start seeing the second one show up while the blue starts diminishing because there's less in that one.
Okay, thank you. And then I guess I had one other comment. And maybe instead of electron cloud, were you calculating wave packets?
Yeah, it's something that dawned on me when I walked into this room.
Okay.
More questions? I have the same one as to Austin. What is the main observable you find after all this machinery?
It's mainly on the reaction rate. We're just watching, and we're trying to compare between these two scenarios and watching. Correct?
And why then do you do Arrhenius plot?
It's just the compare, show it graphically, this data that we achieve here.
Would it be possible to tell that by analyzing reaction rates with Arrhenius plot, you can identify activation energy?
I believe so.
Okay, good. More questions? If no,
Can I give a comment to the poster? Oh, okay.
What?
No?
Is that a yes?
Yeah.
We're waiting.
There's a lot of green space.
Very, very rough draft.
Okay, rough draft. Okay, gotcha.
Yes.
Levi, your shirt also has a lot of green space. So, please collect feedback to your work and implement it towards improvement. So, the next F11, right?
Yes.
So, am I right that next presentation is by Fatima? So please come up front and tell what it is, and I will distribute the printouts. Huh? Well, I keep repeating thanks to Jabet, who is a champion of printing. So if you see nice covered copies, it means Jabet did them.
So first of all, I would like to mention I made some mistakes here. Like in this figure, above homo, it should be low +5 and low +.
You will not notice this amount of information. Do not worry. Give general.
So somebody might ask. So in this research, we we studied electron dynamics along with ground state structure and optical properties of different and silicon nanowires oriented in different directions, and all of the observables are calculated as a function of wave vector. So these silicon nanowires can be used as a functional unit of future nanoelectronic devices. This is the motivation of this research, and Now I'm going to talk about the methodology. So I need to write some equations here. I'll do them next time. So here we used on-the-fly non-adiabatic couplings. Non-adiabatic couplings we got along molecular dynamics nuclear trajectory, and then those non-adiabatic couplings are used as parameters for Redfield equation. And yeah, and the results of this research is ground state structure, optical properties, relaxation rates, Redfield tensors, and now here, as you can see, a band structure figure here. We can see for this one, for silicon nanowire 11100 direction, there is a direct band gap, and for 211 also direct band gap, but for this 111 we can see the indirect band gap. So in order to release photon from electrons.
So may I interrupt you? When you say you can see, honestly I can't. How you really see that it's indirect? Can you maybe visualize it a little bit better? Why you call that your structure 111 is having non-direct band gap?
Yeah.
At which points then?
So here we can see the minimum energy state in valence band.
Yeah.
But for conduction band here is so the two values are not same.
Oh, so you're saying like it's in around your 0.2 for the k equals 0.2. But can you really name this, like what exactly your points for the k? Like, you know,
okay,
the symmetry? How you call it?
So to better understand, I think I can put an arrow.
Like
so
your arrow probably would be also useful. But my question is really like where you have k equals 0, this is your gamma point, right?
Yeah. Mm-hmm.
And the point where you have like this bump in a valence band for the 111 structure with this, looks like, I might be wrong, but it looks like it's 0.2, k equals 0.2. But do you know the name of this k point in terms of like, is it k, l, p, x, w, whatever?
So let me translate the question, and all of us can cooperatively help. So the three-dimensional crystals have electronic structure typically found not for any value of momentum, but in the high symmetry points of momentum, when the momentum is projected along x-axis, y-axis, maybe simultaneously same components in x and y, and they have abbreviations, k, l, x. Would it be possible, on one hand, and would it be reasonable to give such names to points on your diagram, taking into account that it is one-dimensional rather than three-dimensional system?
last part of it.
How many dimensions is in each of your models?
One dimensional. Okay. It is three-dimensional, but it's growing along one direction, z direction.
So can you explain more about the models?
So then it looks like your k is just like you're really choosing this k being either along x or y or z, right? Depending on the symmetry of your system.
Yeah.
Where it is shown or where it is explained or where is equation telling? It is very important.
Well, I think maybe you can just put k wherever, z, right? If it's really having really the periodicity along z direction.
Or maybe the index that you have on the top of each of these three panels. You see the crystallographic direction,
Yeah.
100, and then at the bottom you can put k sub 100. It's a momentum in the direction of growth. And then it will remove such questions.
Here, you mean? On the
For
bottom?
here, it will be k sub 100.
So means
Next
you-
one, it will be K sub 111.
Means you change in K only one directions, you're not really taking all three like in the bulk materials, right? But still would be interesting to know the name of this point, right, in terms of symmetry, for where you have this minimal gap. So, and again, I guess you can figure it out, right? Okay, sorry for interruption, but go ahead.
So now I'm going to talk about the results. So here I placed like density of states for different nanowires and for different values of K vector. So as we can see, for as the wave vector values are increasing, the band gap is also increasing, and it's around the 4K equals 0.5. It's more than 2 electron volts, and for gamma points, the band gap is less than 2 electron volts. For silicon nanowire along 2-1-1 directions, we can see this conduction and valence band moves to lower energy level. And this thing, the band gap is increasing for all of these nanowires.
Oh, may I again interrupted? By the way, when you present poster, of course, you probably will be interrupted much more rather than it's a regular presentation. So I don't see the purpose, and what is really the physical meaning to show each of these snapshots for each K point, right? Because physical meaning coming only from the total density of states. When you sum, I mean, your real dose is coming from all K points, right? So maybe it makes better, and it saves your space, if instead of showing 4 panels for each cases, right, you just have 3 panels, same as you have in for your band structure, right? And show the averaged density of states, means the dose which will be summed over all K points for each case, right? So you will have just 3 figures, red and white.
Okay.
And again, increase of the band gap would be very clearly seen if you put them together for comparison, right? I see, again, you can show, if you might have some reason to show for each K point specifically, if you really have this result somewhere, used somewhere else. So that's why maybe it does have a physical meaning. Do you know, like, is it really having a purpose to show all of them?
Yeah, that is also a question. Yeah, I don't think, because it takes like a lot of space here. So.
Okay, so you just intermediate details, which you probably, it's better to combine and show it more like density of states which can be measured, right? Rather than when you really have in your specific K point. Okay.
And I'll interrupt also. So, and if you decide to keep this density of states in different K points, maybe you may organize data in space so that K point nanowire grown in 111 direction will be separate from density of states for nanowire grown in 100 direction. Otherwise, they're intermixed, and it is very, very hard to understand what is what. So organize, even for the sake of smaller font, it should be organized.
Yeah, I also probably would suggest if you go with kind of combining them, it would be also interesting to compare for those structures where you have direct band gap, and as I understand, direct band gap they have in a gamma point, right? Where you have K equals 0, right? Looks like it's the smallest gap.
Yeah.
Okay. So you probably can again take the average dose over all K points, the total dose over all K points, and then it would be just one curve, right? And then you can put also the curve coming just from a single gamma point, where you have your direct band gap, the smallest band gap, right? Just to compare how much this contribution of other K points is changing if you just do the calculation in a single point, right? And for those structure where you have the interact band gap, right? So then you probably need, actually I don't know how to. So then you need to take those. I don't know how. If it's indirect, how can you really make one figure if it's actually having contribution from two?
On the band structure.
Oh, yeah. Yeah, for the middle one, this would be really not applicable. But for the gamma points, where you have direct band gap in the gamma points, you can just compare how this contribution of other k points changes the density of states. And this question might be important for a theoretical point of view, like people who will do simulations. They might say, well, why should I really do all these k points if I can just do one gamma point if qualitatively the shape of the density of state and the electronic structure is not really changing?
So you mean gamma points from all the nanometers in different?
Well, I would suggest for sure for those where you have the direct band gap, right?
Okay.
Those where you don't have that when it's indirect gaps, then it's kind of unclear how can you really represent it, because here it's clearly you need multiple k points, right? So it's kind of obvious that you cannot simulate the indirect band gap structure without contribution of other k points. But for those where you have direct, maybe contribution of others is not important, and your density of states, again, just qualitatively, will look pretty much similar. You're not missing any peaks, right? And this would be interesting result overall, like technical but interesting result.
And after that, these are the elements of red field tensors. So here again, I showed like for different nanometers or different k vectors. So what I understand here in all of these elements of red field tensors figure, normally the population transfer occur above the in LOMO here, and this population transfer occurs like in figures of like similar orbital indices, like a same or 1 plus 1 minus, almost in all of these figures, so you can see that. Yeah. And most of the population transfer occurs above the HOMO, except some exceptions like this one here. And you get this one and that one. That's that. And after that, here we can see like these green figures. So we can get a relaxation rate from these figures. Initial states were HOMO -4, so 4 levels below HOMO and 8 levels above LOMO. And for silicon 110 nanowire, we can say we can see like holes are relaxing faster than electrons. For rest of the other two nanowires, so in most cases electrons relaxes faster than hole. And so the electron and the holes finally relaxes here. It's this one is HOMO and this one is LOMO. And conclusion, I need to write a conclusion, maybe more references and technology.
That's it? Okay, let's thank Fatima.
I missed, what is the meaning of your red field tensors? Like, what exactly they're showing? You probably told it, I probably didn't really listen.
Population transfer, electron transfer from different orbitals.
Oh, during the, like when you do the dynamics? It's kind of analogous Kaplan.
Kaplan squared.
Okay.
Fermi golden rule for the ray. May I ask a question? So you are finding very, very important data on where the electron relaxation is slower, like here, or quicker, like here, right? And you are going to describe it in many details. Is it possible to correlate this information about how sooner or later electron relaxes with the density of states? Can you tell that if density of states is higher, it will be very quick relaxation? If density of states is lower, it will be very slow relaxation.
Yeah.
Yes or no, and why? You probably wanted to answer because of Fermi golden rule that includes density of state.
So the probability of the available states for electrons to occupy, if the density of states is high, it is like so. If the density of states is high, then the electron has
But you would agree that there is some correlation that is interesting to explore. More questions?
I have a quick question for you. On your density of states between G and H, I guess maybe I'm not seeing it, but it looks like those are the exact same parameters, like 1, 0, 0, k equals 0, but then they're different diagrams. So, was that supposed to be a 0.16?
Yeah.
Correlating with B?
yeah.
Oh, okay. And then I also want to point out too, same thing happens in your red field between F and G.
Good catch.
You have two of the same parameters, but there's differences in the graphs. So
this is
between F and G, there's 1, 0, 0, k.
Oh yeah, it should be 0.33.
Okay.
I
No, that's right. I just wanted to double check to make sure.
Any question?
Yeah, is the cap point for density of a state is choose arbitrarily, or just there have some significance with the band structure? I'm just wondering because if 111 doesn't have a direct band gap, why you didn't choose that cap point with showing that lowest lowest unoccupied orbital?
You mean how I selected the?
At which cap point is the LUMO state is lowest in the 111 system?
Oh.
But that's not in the zero maybe, right?
100, you mean?
No, 111 system.
Oh, yeah. So the conduction band?
Mm-hmm.
No,
Lowest
it's not.
conduction
That's
band
why-
is shown in the DOS or not?
So that's why it has indirect band gap.
Yeah, but at which cap point? Is that shown in the DOS?
Yeah, no, it's not mentioned like exactly. But I think it's maybe around.
And is that energy difference is significant because it seems like at the gamma point and other lowest one is very similar energy, or energy difference is very, very small.
Can you show it?
I mean in the conduction, in the indirect band gap, indirect one. At the gamma point on zero, cap point is 0, that energy and whatever the lowest one you think, that one is very close. I mean energy difference is very, very small.
Yeah. I mean, like if you look on the gamma point,
Yeah.
this indirect, the
Indirect
difference
one,
is
yeah.
very small.
So maybe required momentum, electron momentum would be very, very small to relax down from the gamma point.
Yes, yes. If the dispersion curve is has very small curvature, the density of states near the band edge is high and relaxation is facilitated. It will be much quicker.
Okay. So that means it should be comparable with other true system. Like.
Mm-hmm.
So, is it needed? Is momentum has the momentum be conserved when you do the relaxation? In other words, is it possible that you're relaxing from this electronic state to that electronic state, and you're changing the momentum? Let's say you go from gamma from 0 to the electronic state which having the momentum 0, 2, or whatever your index is there. Or you really have to conserve the momentum, means if it goes to this electronic state, the K momentum of the state should be exactly the same as K momentum was in the initial state where it jumped from. Do you know?
I didn't understand the question.
Would you agree that momentum is conserved?
Yeah, momentum is conserved.
But it
For the relaxation?
So
you cannot relax through the phonons having different momentums?
So
You can.
Wait. Now I will answer on the to protect the other cursors. This is work in development, and the code with transitions. Yes, in the nature there are non-radiative transitions with vectors, with change of momentum, where the difference in momentum is dissipated away in form of phonons with non-zero momentum. Here in this code, phonons do not have momentum. Therefore, there are available transitions only between bands with conservation of momentum.
I understand that this is a limitation of your approach, but my question was, in reality,
In
right?
reality,
So the momentum is not conserved,
In reality, momentum is not conserved.
and you actually has to implement in your model this additional channel where you have jump between electronic levels, have like, as Vit is showing, really kind of following not the same momentum as you're showing in your green curves, right? But you also can jump between levels with different K momentum. So this channel is not really included into your model, but it exists. And how is it important? Can you neglect it or not by this mechanism?
Cannot be answered before
I mean, there are
writing
no
next piece of
literature
no.
so far.
And there are no calculations. It is a challenge of the community.
Okay, good.
More questions? If not, thank Fatima once again. And we have two presentations for the. Please, Fatima, please collect feedback. Everyone who were given written feedback, please return it to Fatima. And we have two presentations for the remaining 20 minutes. So the next presentation is by Dr. John Fogel, and here's his first slide and printouts. And the organizers of symposium looked at his poster abstract and asked if he would agree to present it orally. And to my understanding, he accepted this offer. John, please start telling, and I will assist in changing slides.
Okay. Well, does it just work if I control it?
Sorry to interrupt you. So actually, I think they have a pretty limiting time frame for the contributing talks, only 15 minutes. With you probably want to save at least 3 minutes for questions. Should we really take 12 minutes for the presentation?
Maybe even 10 in current circumstances.
10, at least 12. Okay.
Yeah. So, okay. So you guys can see my slides on the screen?
Yes. Yes.
Okay. So, in this short period of time, what I'd like to discuss today are looking at methylammonium iodide perovskite materials and how we can modify these materials to increase the benefit in photovoltaic and optoelectronic applications. So since this is a PDF, you didn't see the images that are underneath this one. But the motivation behind looking at these materials is in this bottom right-hand corner of the plot that's kind of covered up on your screen, there's a very dramatic rise in efficiency using perovskite materials. And so in the last few years, 5-6 years, they've gone all the way up to over 22%, which is extremely fast. So that's why people are extremely interested. So to look at two different types of modifications in these materials, we wanted to take a look at in a bulk material, which is shown on top. And we also wanted to look at what confining the material spatially into a quantum dot would do to the electronic structure. So in this top figure, you can see two images. One is a two-dimensional cut showing where the vacancy is in the center of a supercell, and then the three-dimensional model with the vacancy also in the very center of this. And so to show chemical formulas for these structures, you can see a perfect material, a lead vacancy, and then the lead vacancy +1 and the lead vacancy neutral, which are charge corrected for the removal of 2 valence electrons with the lead atom. And so the bottom just shows the quantum dot, which is composed of 3 unit cells of cubic phase perovskite material. And so in looking at the properties that come with these two types of distortions to the material, we want to take a look at them in a number of different ways. And so primarily we'll be working in VASP with the PGA PBE functional, but we want to use a number of the different builds VASP has to offer to look at how different properties affect the electronic structure in total. And so we'll look at the standard method. We'll look at trying to take into account multiple K points for the system. We'll look at spin polarized DFT, and we'll also add an element in using non-collinear spin DFT to account for spin orbit coupling effects in the electronic structure of the material. And then I'll present a little bit the microdynamics and adiabatic coupling, and then the time-dependent density matrix, which will produce a number of observables, which will help us identify what effects these effects in spatial confinement has. So in identifying the electronic structure of the materials, we can find the solutions to the one-electron Kohn-Sham equation in solving for these eigenvalues and eigenvectors. But moving forward in a basis of Kohn-Sham orbitals, what we want to do is we want to be able to look at electronic transitions and optical properties, which we calculate as transition dipole moments. And so in using these eigenvalues and eigenvectors, we can solve these transition dipole moments, both in the standard build, the spin unrestricted DFT, and then in the non-collinear spin DFT. And so with the optical properties that we have, we can use these transition dipole moments to calculate oscillator strengths for specific transitions between 2 specified orbitals. And from that, we can calculate the absorption for that specific transition. And we can also characterize the ground state electronic structure by comparing density of states, utilizing all of these different methods. And so in going from our ground state to our dynamics, we do this in such a way as we do thermalization calculations to interact the chemical system with a thermal bath to allow a temperature equivalent to an ambient temperature that might be found experimentally. And so we calculate microdynamic trajectories classically in the sense and use the ground state microdynamic trajectory to update the atomic positions, which get used in our on-the-fly non-adiabatic coupling calculations. And so these coupling calculations allow us to look at the wave function changes, the wave function overlap from one time step to another, in goals of equating molecular motion with electronic transition. And so in taking these non-adiabatic couplings, we can take an autocorrelation followed by a Fourier transform, which produces these components of the Redfield tensor, which is then looking at the square root probability transition between two specified states, similar to what would go into Fermi's golden rule. And so this portion of the Redfield tensor is a dissipative portion in solving for the time-dependent density matrix. And so this Redfield portion is coupled with a quantum Liouville portion for electronic density propagation, allowing us to use the Liouville and Redfield superoperator acting on this density matrix to produce, oh, one too far. Maybe that's what you, maybe that's what's in the slides. Okay, so I guess that's what you have in this PDF. So looking at how this time-dependent density matrix is propagated and allowing us to look at how charge carriers can move in energy and calculate rates of non-radiative relaxation, radiative relaxation within the materials. And so the first aspect in the bulk material was to look at the role of a lead vacancy and how it's going to affect the optoelectronic properties of the material. And so in looking at the density of states of the material, we noticed something initially right away. So this top set of three figures corresponds to the density of states calculated at the gamma point for the closed shell perovskite materials. And so you can see in the perfect material on the left, there's a very large band gap. In the middle image, top middle image, you can see there's an additional unoccupied state now that there's a lead vacancy. And then once adding two additional electrons, you can see that there's no longer an unoccupied state, and it's also shifted to the top of the valence band. Now, one of the issues we had with this was the band gap for this is extremely large, and it is not congruent with what is found experimentally. And so looking at the band structure of the materials, we know that there has to be some inclusion of multiple K points of the material to correctly account for the band gap of the material. And so what's shown on the bottom three panels is the density of states, including all K points within the mesh in red, and then the single gamma point in blue of the material. And so one thing here that we found to highlight was the fact that even with the inclusion of all these K points, we still had the vacancy state maintained in the material. And so looking at band structure calculations, you can see that across all K points, the vacancy state remains fairly similar. But we're also interested to see that the increased energy difference between the different bands in the valence band changes in shape and energy dispersion in moving from a lead vacancy to a charge-corrected system. And so this can also be seen in the absorption spectra for the material. So on top are the lead vacancy and then the charge-corrected singlet. And so these absorption images are very similar to what is seen experimentally, where you have an onset somewhere close to 800 to 900 nanometers, and then absorbing higher. And so the bottom two panels show absorption, with each line showing the absorption based on one single K point. And so you can see that for the early onset or absorption onset is highly dependent on one specific K point, with the others contributing in the higher energy region. And so this is something of further development. And so there's going to be a poster on a specific night with, you can talk to Fatima, looking at how K point dispersion may be included in non-adiabatic calculations. And so in moving to the open shell system of the material, we're now looking at the spin polarized DFT calculations and trying to find which spin projection may be playing a larger role in the additional unoccupied states present due to lead vacancies. And so they're presented both for just the single gamma point again, but then the right two panels are presented for the entirety of a K-point mesh. And so the main changes or highlights from these is that for the lead vacancy plus, you can see that there's a beta spin projection unoccupied state in both of the systems. But then when looking at the K-point mesh, you can see that this unoccupied state gets pushed in the beta spin projection to the top of the valence band. And so the importance of these unoccupied states for the specific spin projections are that it's going to directly affect the time scale for non-radiative relaxation in that spin projection. And so by having these unoccupied almost trap states, we can increase the lifetime of a specific charge carrier if it happens to be in that spin projection. And so in looking at the electronic structure utilizing the non-cleaner spin DFT, what I'm showing here are the DFT absorption spectra and also the DFT plus spin over coupling corrections absorption spectra. And so in looking at the higher energy absorption transitions, you can see that there's a systematic shift of about 1 electron volt in all 4 of the systems. However, in the lead vacancy 2 plus and the lead vacancy 1 plus, you can see some lower energy transitions that show no shifting between just the standard DFT and the spin orbit coupling enhanced DFT. And so with this type of comparison and similarity, we can use this as an assumption of moving forward with the spin polarized DFT to be something that's qualitatively correct and saving computational cost. And so this work in going forward with spin orbit coupling, it's also something that has been done previously by Dr. Han. And so something that presented last year and can be discussed further with other colleagues. And so in looking at these ground state structures, we saw something unique when we added this lead vacancy and also when we had a lead vacancy plus 1. And so we want to look at the specific Chem orbital energies and how they fluctuate along the molecular dynamic trajectory. And so from plotting these Chem orbital energy fluctuations, we can see that for one system, this lead vacancy 2 plus, there's a great fluctuation. So there must be something possibly of interest happening. And so in focusing on this specific system, switching the wrong one. We took a look at what might be happening. We found that there was an I2 formation within the material that was changing the distribution of electron density and rearranging the HOMO-LUMO orbital indices within the material. Okay, I think I'm already over time. So in looking at the total non-radiative relaxation dynamics within the material, what's important to highlight is that with the addition of this unoccupied state, either in the band structure itself or in the alpha or beta spin projection, the addition of this unoccupied state produces a trap state that takes a much longer time for a charge carrier to relax to. And so this type of long-lived relaxation can be extracted with a higher photovoltage for device, or be ended up transporting to the surface or something of that source for a photochemical reaction. We also looked at what happens when you spatially confine the material in a quantum dot. And so using the same methodology, we wanted to focus in on just a few of the possible photoexcited processes, and specifically adding in the calculation of multi-exciton generation and how that competes with non-radiative and radiative relaxation mechanisms. If we can use the spatial confinement to increase, say, the process of multiple exciton generation, it can be applied for a higher efficiency within a solar device. And so within the quantum dot itself, looking just at the non-radiative relaxation times, we found some interesting trends for the material in such that for higher dissipated energy amounts, we saw something similar to a gap law of a linear trend in timescales. However, once we got down to a lower energy dissipation, there was a unique increase in time instead of what we would normally see go to a very, very short time. And so I'm looking at the possible overlap of specific orbitals, introducing unique transition pathways at these lower dissipation energies can produce a longer time scale, allowing other mechanisms to be more prominent. And so our collaborator who worked on calculation of the multiplex time generation did this in such a way of using DFT calculations with HSE06 hybrid functional in place of GW single particle energy corrections, and plugged them into the Bethe-Salpeter equation for solutions to the exciton wave function. I'm just going to quick skip to the end, just so there's some questions. So the conclusions, in looking at these two different systems, we found that in the quantum dot, we had slower relaxation for non-radiative processes, allowing unique processes such as multiple exciton generation be more prominent, therefore enhancing the total overall efficiency of a device potentially made with these quantum dots, which was the end goal. So I'll answer a couple questions now before it disconnects.
Okay, thanks, John. Any questions?
What exactly was the main purpose of your investigations?
Well, so the main purpose of the investigation.
Bulk versus quantum dot?
Yeah, so what happens, well, there were, I guess, two specific goals. One was, yes, what happens in relative non-radiative and radiative relaxation rates when turning a quantum dot, spatially confining it? And can this enhance other relaxation processes to occur? The second portion of this was these materials are, when they're made, it's hard to make a completely pure material. And so in the environment in which a lead defect exists, how is that affecting different relaxation mechanisms and the resulting radiative and non-radiative rates?
But then your conclusions do not answer any of these questions, from my understanding.
So,
well, except the first one. So you're just saying in the bulk it's faster in quantum dots.
Okay, so
right?
Yeah, this is not up to date with what my slides have, but yeah. So there's a few other points on the actual PowerPoint presentation, I guess, than the PDF. But yeah, so the points are: using a quantum dot allows for a new relaxation mechanism, specifically multiplex generation, to occur because of the time. The lead vacancy. This lead vacancy creates an additional state, which allows for long-lived lifetimes and possible relaxation pathways to occur, which wouldn't have been available in the pure material.
Well, I'm a little bit confused because, again, on one hand, you're saying that quantum dots slowing down the relaxation, and it looks like it's beneficial. Then you say other relaxation mechanisms, and then you're talking about the impact ionization, right, or carrier multiplication. Carrier multiplication is governed through the electronic couplings rather than really phonon couplings. So why do you call it a relaxation processes overall? Without the electronic coupling, these processes will never happen, right? So phonons, even if they contribute, they are not the major thing in these processes, and consider carrier multiplication as a relaxation channel sounds a little bit awkward for me.
Okay.
Am
Am
I doing something wrong with it? Like, where is my confusion? what is wrong with my speculations?
I mean, it could be that I shouldn't lump them all together as a relaxation mechanism. Maybe I should put it as would you also consider it an electronic relaxation or an electronic transition process?
Yes, electronic transition, or you can find a neutral verbal formula, like photo-induced pathways of excitation.
I would say you have photodynamical processes, right? One is,
Mm-hmm.
and they're actually competing with each other, and probably one is really having a negative impact on the other. So if you want to increase efficiency of carrier multiplication, you probably need to reduce the efficiency of relaxation through the phonons, right? So you usually, actually, they're competing processes, and maybe you really need to put the story on a competition rather than make them to be kind of sounds like, oh, it's the same relaxation just with two carriers at the end.
Right. So, okay. So I'll modify this slide, but that's part of it. All of these are competing with each other, and because it's a quantum dot instead of the bulk with the energy dispersion of the states, I'd hopefully slow down that non-radiative, allowing the multiple exciton generation to occur on just a little bit wider time scales. Yeah.
And we have one more presentation today. So if there are no more questions to John, questions 1, question 2, question 3, let's thank John once again. So I will represent John and collect the feedback, written feedback. And John, can you please complete your content sharing?
Yep.
Thank you. So, last but not least for today presentation. Okay, last but not least, presentation by Dr. Yulun Khan. Did you distribute your? Yes or not? Okay. And I would consider it as a dessert of our today's meeting because his poster contains very fresh and new ideas that all of us should enjoy or may enjoy.
Okay, so the hypergolic propellants. Okay, so the hypergolic propellants typically consist of fuel and oxidizer. So the hydrogen and the hydrogen derivatives can be used as fuel, and nitrogen dioxide or dinitrogen tetroxide can be used as oxidizers. So when these two components are on contact, there will be spontaneous ignition. And there have been many studies on these systems, but it is found the activation energy for this reaction is very high. It's about 0.4 electron volts. So it is unclear why this spontaneous ignition happens at room temperature with such a high activation energy. So in this study, we want to figure out what's going on. So first we use ab initio molecular dynamics to simulate the chemical reaction of mono methyl hydrogen and the nitrogen dioxide. After that, we do wave packet dynamics. Because one problem in ab initio molecular dynamics is classical path approximation. So in this approximation, the electrons are treated with quantum mechanically, but the nuclei is treated classically. So in this specific system, we suspect the quantum tunneling is very important. So we have to use the wave packet dynamics to solve this problem. So this is my computational detail for wave packet dynamics. I'm going to skip that. So here's my model. So this is a geometry optimized model. So here we have the monomethyl hydrogen molecule, and outside we have 8 nitrogen dioxide molecules. And this is the final step of ab initio molecular dynamics. So we can see there are some new species, like this is methanol, and we have HONO like here. So by the way, the ab initio molecular dynamics is run at 2000 Kelvin. And here is the energy diagram extracted from ab initio molecular dynamics trajectory. So this is the first hydrogen transfer reaction, as I show here. This is the second one, this is the third one. So in the first one, our calculation shows the activation energy maybe it's like 0.5 electron volts, so a little bit larger than the literature value. And to get this spectrum, actually we use a post-processing technique. So basically we only keep species participate in the chemical reaction. We intentionally remove unparticipating species, and then we run single point energy calculation. And here I show some data for beta charge. So basically, our observation is the hydrogen being transferred is actually proton instead of neutral hydrogen atom. And then here, it just shows some number of fragments during the trajectory. So we confirm we have the HONO species, and we also have other species like the nitrogen gas. And here is the results for wave packet dynamics. So one input we use for wave packet dynamics is the potential from molecular dynamics trajectory. So basically we apply some technique to convert this diagram to this one. Here the energy is plotted as a function of reaction path. And after we got this one, we can run wave packet dynamics. So here is a snapshot for wave packet dynamics. So the red curve is the initial state, and the green curve is the final state. And here, the blue one is the potential energy. Okay, here is one of the results. So basically, at this time, so we can see the splitting of the wave packet. So that means at this time, some has already passed the barrier, but major just reflected back. And this is a distribution of probability. So we found maybe 18% has already passed the barrier. And this is a Arrhenius equation plot for different initial conditions. By different initial conditions, I mean the different initial momentum. So by using this fate, we can actually find a Arrhenius activation energy. And actually this Arrhenius activation energy is way lower than the activation energy defined from molecular dynamics trajectory. So that's the reason the spontaneous ignition happens. That's it.
Okay, well, thank you, Lun. Interesting presentation. There are questions.
Okay. So, what is the density of your initial system? Is it liquid? If you compare a real system, is it liquid or gaseous phase?
I guess it's gaseous.
Gas phase. And all of your fragments, those are also gas, right? So if it's produced the hydrogen or all other gases, the pressure is supposed to be increased significantly after the going on with the time. Because it's creating more gaseous fragment, it will increase the pressure significantly, and the equilibrium coefficient also depends on the pressure. So it will change the reaction rate with the time.
I say point, but why it matters?
So I'm just wondering, did you get anything like with your
Why the
study?
pressure would be
with
changed? I missed this point.
Yeah, pressure would be increased because it's creating the more gaseous number of according to the Avogadro rules. Each molecule, each mole will produce the same, fraction of gas.
But number of molecules are fixed there.
No, number of atoms are kept constant.
Number of molecule is increasing.
Well, it doesn't matter. Number of compounds are the same.
No, if number of
Your
molecules.
pressure will be not increased if you have, let's say you have 5 atoms and creating one molecule from 5 atoms, right? So why are you expecting the pressure will be increased?
Because number of moles increasing.
So degrees of freedom.
Actually, it will be backward because now you're creating a molecule means you decreasing the size, right? So before they were like that, now they're taking only this space.
Yeah, so when you make the molecule, your volume is decreased. That's what you just said, correct?
No, I know you are
Yes.
making more number of molecules. That means volume increasing.
I'm saying what Svetlana said was if you have atoms and you make a molecule, the volume decreases. Correct?
Now
Is
we
that what
have
you
a
said,
big
Svetlana?
molecules.
The density is probably changing, but not really the volume. You can fix volume wherever you want to.
So,
Yes, but if
the question by Jabbat is, will the results be affected by the fact that during combustion, products create heat, higher pressure, and conditions of continuous reaction are changed?
Changing.
But the volume of simulation cell is fixed, and even if the pressure is increasing, it is included in the ab initio data that are used as a parameters, as parameters of this stuff here. So those data are computed ab initio with fixed box with changing pressure. So it is not single molecule in vacuum in Gaussian. It is high density. It's close to liquid in the periodic boundary condition. Does it satisfy?
Dimitri,
Yeah, that's what I'm.
Yes, Levi.
so Yulun, your top figure in the middle, were those computed when you took out everything that's not in the reaction?
Yes.
Because I thought that's what you said.
Yes.
So wouldn't the density then change as your number of molecules are in the reaction stage, which then means that you're not at a fixed number density?
Great question, Levi. Thank you.
I understand your question, but why this is a problem? Why it matters?
Because it comes back to the question of Jabez. If your response to it is VASP uses the same simulation cell and we get this out, then by taking out the molecules, you're decreasing the pressure by removing atoms.
Levi?
So
Yeah.
Or if you want to speak, please go forward.
So actually there are 2 steps. The first step is just from molecular dynamics. The second step is to post-processing. So in the post-processing technique, we remove participating species.
And what do you get from that?
So that we can compare the energy difference.
So then is it per atom, per molecule? Because depending on how many how many things have reacted, then that could change the height of the barrier. Right? If you're just taking the total energy and you keep adding atoms, the total energy is obviously going to go up.
No, the atom is fixed.
No, I mean, he meant the total number of molecules, maybe not the atoms.
Well, let me comment. It is really interesting direction of thinking that contributed by Levi, and we can address it maybe by 70%, not completely. It's really interesting. So what we can address by now, I'm just doing it quicker. Dr. Khan knows this. If we keep all surrounding atoms in the simulation cell, it will bring a lot of noise. So we need to remove them to avoid random fluctuation. And second, Levi doesn't hear it, but we have the recordings. And second, these, please correct me if I'm wrong, the structures which you keep upon removing the rest of atoms do keep memory about the pressure because their interatomic bonds are frozen as they were created during the pressurized conditions. So is it so? Or not quite?
I don't get it full. Things. Can you say again, please?
So at each stage in the dynamic process, you freeze it, remove all atoms, take an energy, and then continue with all the atoms in the box and then freeze it again?
That's an independent process. So for the first time, we just run molecular dynamics, and there are lots of chemical reactions going on. After that, we do.
You just
like
zero in on one of the reactions and
Yeah.
look at the energy at each point of
Yes.
just the contributing molecules.
Just
So
contributing
the
molecules.
bonds should be the same regardless. Or the energy, because it feels all the atoms, so yes, right?
I guess the whole point is just to remove the interference with other species.
Another thing is for that, what's the name? What is his equation name? This common one. Arrhenius, yeah. Isn't Arrhenius is a fixed constant pressure equations based on? Did you try the other one? What's the other one? Constant volume one?
Why are you looking at me?
Is it with physics?
So, Jabat, would you please write your question, because it was promised that we will stay here until 6, and we are about 20 minutes after, and some of us, of you, may have plans for evening or just got tired.
Arrhenius just Arrhenius equation is based on constant pressure. Sorry, constant pressure, and they have another equation with a constant volume. So you can use that equation.
Write it down. So please write down all your questions and submit to authors. Let's thank Yun and all speakers of today once again. And next time we will go into the iteration. Everyone who presented previous week, we will present again in the same order, the improved version. And those who presented today, we will present in 2 weeks. And in 3 weeks, we all will be on the beach.
How many people we have then for next time?
6, maybe 7th. We have 6 and 6 plus 1, and plus 1 never presented.
So would you like to do it here?
Yes.
So do you want to do it next? I mean, incoming Tuesday in a week?
That would probably be the best option for me.